Well, hello friends. Today we are going to work on the system monitor a bit, and we're going to have to do some kernel stuff to get what we want, because what we want is to be able to see all the currently running threads here. Because a big issue right now is that you can see the Windows server here, for instance, taking up some CPU, but what you don't see is the fact that it has two threads. It has a secondary thread that's generating this little CPU usage graph up here. And some other stuff in the system also has multiple threads, like the audio server, for instance, has a secondary thread. And the only way that you can currently find that out is that you can go here and look at the stacks for that process, and you can see that there is a thread 0 and a thread 1, and that there's stuff going on here. So this is definitely something that needs to be improved. So I think today what we're going to do is that we're just going to make it so that all the threads show up here, and we're not really going to do anything fancy. We're just going to make a separate, I think just a separate line for multiple threads. So, oh shit, I didn't even know what happened there. We just hit a reboot. That's really bad. Frick if I know what that was. Let's just check right quick where we crashed. Was not expecting that. We died in, I mean, it looked like a triple fault. Enter process paging scope. All right, well, something went wrong there, but that's not what we're going to work on today. So we're just going to ignore that and go straight to the showing the multiple threads. So the file that everything in the system monitor comes from is in the /proc file system, and it's called all, and it's this JSON file. So if we use JP to print it and pipe it to more, then we can see that, actually let's do it this way. So each one of these is one process, and in every process we only show the main thread. So each one of these is really like the main thread of a process. So I think what we're going to do is we're going to, first thing we're going to do is we're just going to go and change that file so that instead of each process, it will show each thread in each process. And here, by the way, you can see how we build up one of those JSON files in /proc. It's pretty neat. So we loop over all of the processes which are extracted from the process table here. And then for each process we call build process, which just creates a new JSON array. Oh no, a new object, sorry, a new JSON object and an array of objects. And adds all of these fields. So I think what we can do here is we can just make a sub object or like a subarray. So we can make an array of threads. And that would be something like process object add array thread array. Wait, frick, how do I do this? I have to have the name of it, right? Yeah. We're gonna call it threads. Okay. And then, let's see, auto threads. Process dot, wait, we have a process. How do we get all the threads for it? For each thread? Okay. So for each thread in this process, auto thread, I mean, like this, I guess. Hopefully like that. Okay, so thread array add object thread out, or Okay, so thread object, and then we have to populate that thing. So thread object, add tid, that's the thread ID. So thread.tid. And what else can we find out about it? I guess the number of ticks, which is how many times it's been scheduled, or how many like timer ticks it has run. Each timer tick is 1 millisecond at the moment. What else can we show about a thread? Thread, I guess we have the priority. We have state, because currently, I guess we should look up here. So we see that there are various things that we just take from the process.main thread. So anything that we're taking from main thread, we should really be showing for each thread instead. So this guy right here, times scheduled. Let's put that down here. And the state. And what else do we have? Ticks we already got, so the priority has to move as well. And I guess syscalls counts, they could be per thread instead. Currently we track the number of syscalls per process, but we could change them to be per thread. We could do the same thing for faults as well. When it comes to memory usage, that's per process, because a thread does not have its own memory space, right? It's shared between all threads in the process. So anyways, let's just take these things right now and just get a feel for what we end up with here. So array, add object, process object. I think that's pretty good. Let's see how this looks in practice. If we just build it. That didn't work out. For each thread, void value not ignored. Oh shit. Yeah, I have to return an iteration decision. To inform for each thread that I want to continue iterating through the thread list. Okay, now this is obviously SystemMonitor is going to be all broken now. I think it might not even run. It does run, but look at how bad it looks. Jesus, everything's all weird. So, and CPU usage going crazy because this CPU usage thingy here is also based on the this file. So, but let's just have a look at proc all. Type to more. Should have made that a little bit bigger. So threads. This guy here has no threads because it's the kernel process. Right. So that's special. That's the idle task. It doesn't have any threads in it. I think that's normal, a little bit weird. Okay, and then we have. This is JP, the JSON printer program that we're looking at right now. It has one thread, tid 0. It's been running for 4 milliseconds apparently. This is really neat. So we can see audio server. Audio server has 2 threads, right? It has thread 0, priority high, and thread 1, priority normal. Already I'm learning interesting stuff, because look at this guy. He's been scheduled so many times. So there's probably things we can learn about things here. Anyway. Okay, so now we gotta unbreak all of this stuff, right? Because the CPU monitor, this is the Windows Server CPU monitor in the top right corner. And the way that it gets the CPU usage is that it calls the C process statistics reader. Now, lucky for us, we actually have a convenience class that parses proc all. So, and I noticed that this thing should probably have unistd.h to make all of this warnings go away. Yep. And then, anyway, so this thing is for parsing proc all. So we are going to have to parse things a little bit differently now, because see process statistics. I guess we're going to want to, let's see, what do we do in the here? In this one, we grab all the process statistics and then we iterate over all of the processes and add together a number of times scheduled. So I guess what we should be doing is iterating over all of the threads in all of the processes. So I'll do this it.value.threads. And I can tell that this is going to be a little confusing here because PID0 is the idle task in the kernel process. So we're going to have to, because right now in the JSON it showed the PID0 as having no threads, so we're going to have to fix that somehow. But basically, if we encounter PID0, then we're going to consider that idle time. Otherwise, it's busy time. So then, let's see, JT. Okay. And here, let's add a thread vector. So vector, see threads, or just sticks, something like that. And we had the TID, and we're moving some stuff over, so these, this, yeah, priority as well, right? Okay, so then, oh yeah, right. And then we have to make sure that this thing populates that thread object. So this is the code here that reads the JSON file. So now we can tell from the warnings that we have to do something about these lines. So we'll just put these at the end. Process object get threads as array. So then we'll say for auto thread and threads, and then see thread statistics thread. I guess we should call it thread object here. This one we can call thread array. And I'm not allowed to iterate over an array like that? Alright. What can I do then? Can I do thread array for each? Okay, that's good enough for me. Value, I guess. Thread. Okay, and then we'll just say thread, and process.threads append thread. Maybe even move. Okay. And here we want to look at thread object. So the thread object is going to be the value thingy, value as object. Yep. And let's also get the TID. Get TID to U32. All right. I think that's pretty good. Now we should probably have that populated, and let's go and see about that procfs thing for the PID 0. That's the way that we add that is this way, because normally when you do when you fetch all processes, then it deliberately excludes PID 0, and if you actually want to see PID 0, you have to go and fetch it yourself through this pointer here. And this thing does not have any threads. But it does have a main thread. So wait, it does have a main thread. Why can't I get that out by calling for each thread on it? For each thread. Let's see. If thread PID is my PID. Oh, maybe the PID of the wait, what the heck is the PID of the of the kernel process main thread then? Now I'm confused. So this is how for each thread works. It just iterates over the global thread list, looking for any thread that has a certain PID. So where do we make the kernel process? In scheduler initialize. We make the kernel process, and that does create a main thread. But what's his PID then? If we look in the process constructor, where do we create thread? Right here, new thread, this, okay. Oops. M process, blah, blah, blah. Oh, if M process PID is not 0, then we add it to the thread table. Otherwise, we don't add it to the thread table. Ooh. All right, all right. So this is scheduling related, so we don't want it in the scheduler in the thread table, because we don't want the scheduler to ever look at and consider the kernel thread for any scheduling, because it's special. It's used for the idling, so we want it to be excluded from all the algorithms that actually look at the thread table. So I think maybe we're gonna just have a little special situation with this. So I think we will maybe we will special case for each thread. So when you call for each thread, we can do something like, if my PID is 0, callback main thread. So special case the kernel thread, since its main thread is not in the global thread table. Note. Okay, so now this should work. Because now the threads array in the JSON should have the main thread of the kernel process. But we have screwed it up somehow because we can't just call things like this. Why not? Because it's const. Discards qualifiers. Well, my bad. I'll just do it this way. The reason it's const is because this frickin' iteration helper is const. I don't know why it's const, actually. It seems like if you're calling for each thread on a process, it seems like you might be doing decidedly non-const stuff, so I'm not sure why I made that const. Okay, so we're still looking pretty screwy up here, but let's take a look at the JSON at least. Okay, and let's do more. So now we can see the kernel thread up here. It has one thread, PID0, TID0. It's looking pretty good. Now we're probably gonna have to rebuild everything just to make sure that we get the updated version of the proc all parser. Yeah, okay, here we go. Process model. This is the code in the SystemMonitor. And of course, it doesn't find all of these things that it expects, which makes perfect sense because these are per thread now. Okay, so I was thinking that we would just, instead of having it be a list of processes, we would just make it a list of threads. I would make it simple for now. So I think for all processes, maybe we'll do something like this. For auto it or JIT it value threads, and then this will really be more like a thread state, honestly, because we'll make a new one for each thread in the process as well. But we'll say state times schedule is this one can really be called thread, I guess. Let's just rename this to thread state. Entityd, okay. And then we really want to surface the TID in the UI. So we're going to need to add a column for it to this class, this process model class. We're just going to add a TID. I guess right after PID would make sense. So let's see, PID. Have to do a few of these. La 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 la. And this is more of a thread now, actually. So we'll rename that. And just making sure that we surface it in the model everywhere. All right. And I guess we can rename M processes. Where is it? Here. This thing process, we'll rename it to thread. And this thing will be named M threads. Okay. This is actually like legit going to be fascinating because I've never seen what all the other threads are doing. They've been hidden from me this whole time. Process state widget. What's wrong with you? Data.state. Oh shit, right. So this is in the Hack Studio program. It shows the state. If you're like running a subtask, then it shows the state of that process. So I guess here we can, let's just do like threads first dot state, just for simplicity here. Because this thing is a very half-baked feature anyway, so it's okay. It's definitely not final in any way. You rarely even see it. It's just this thing that flashes on screen when you run the program that you're working on. So in PS, let's just show the main thread state for now. So threads first. But otherwise, PS should probably have a way to show threads as well. We have top. Totally forgot about top. Top program. Should we divide it up by threads as well? You know, I'm feeling a little bit lazy. Let's, no, let's not be lazy. Let's change it up. So instead of process data, we'll have thread data, and we'll say for all processes, we will do auto or auto thread and threads. Thread data. So let's see. And what the frick am I looking at here? Wait, thread data contains process statistics. Oh. This has been annoying. How about we just compile that out for the moment and move on to the next thing. That did not go very well. The process statistics reader is totally messing up. Why? Process statistics reader. What is going on? What was the first error that we had? Because I guess this is in Windows Server. And then Windows Server again. Oh, because it's restarting now. Okay, so the first crash is in get all at this specific address. So let's just take a look at it. What's wrong? Vector at. to number. Okay. Vector at. Is it that? It's freed memory. So what's freed here? We're doing something stupid, I bet. Like this thread array. It's probably a temporary or something. So maybe we just have to make a copy of it. It's dumb. What are you gonna do? Okay, so now we got this thing looking pretty okay. Let's look at our system monitor. Well, I see TIDs, but I don't see audio server thread number 0. I just see thread number 1 here. So there's only one, although now we can see the CPU usage is going up, which is quite curious. So let's see, what are we going to make of this? We definitely are not showing all of the threads here. So why are we only showing one? We're going to have to look at the process model. So I guess the number of rows is the PIDs size. Well, that doesn't seem right. PIDs. So here, like, let's say TIDs instead, right? But wait, why do we have a PIDs thing even? And I guess we need something else to uniquely identify these things. So we're gonna need like a struct PID and TID. PID and TID. And then we're gonna need some frickin' traits for it. Pair int hash traits. I'm just gonna steal these from somewhere. I should probably make a pair class at some point. So let's make some hash map traits for PID and TID. Value. Value TID. Alright, so there we go. PID and TID. Oh, we gotta put these in the global scope. Just a second. There we go. Now we can use PID and TID as a map key here. PID and TID, and likewise with these PID and TID. PID and TIDs. We can leave it like PIDs for now, I guess. What is MPIDs used for? MPIDs. Okay, so we're gonna have to look at this a little bit. At this point, it would be convenient if things worked like some other systems where every thread has a unique PID instead of having a PID and a TID. Okay, so here we want to look for, when we're doing a lookup here, we want to look for not just the PID, but the PID and the TID. And likewise here. I'm just instantiating temporary PID and TIDs here. Okay. And then live PIDs. What's live PIDs? I guess it's gonna have to be a PID and TID as well. So threaded. Patented. And then if it is not 0, okay. I think we got everything. Let's have a look here. Nope, not quite awesome because I forgot to. There's no operator equal for patented traits. Well, I can implement an operator equal. Just watch me. Tid is other tid. Boom. I wonder what would be like a really good UI for showing threads. Maybe some kind of tree view or something like that, where you could see the threads inside of a process if you open it up. I don't know, but what do we have here? Oh, looky, looky. Now we can actually see these things. So let's sort by PID, and then you can see audio server, thread 0 and thread 1. This is the mixer thread. And it's actually like doing stuff all the time, because what it does is that it sleeps, I think, for 10 milliseconds, and then it wakes up, checks if there's something to mix, and then falls back asleep. And I've just been postponing doing something about that because I guess because it was never staring me in the face like this, like it is now. So that's actually really good. And then we have this thread here in the Windows server, which is probably the, I mean, it is the main thread. We can see here it's tid 0. So it's like the thread that's drawing the screen. And then this thread here is far less busy because it only wakes up every 1 second to populate this thing here with data. So it's not very busy. Now, it would be cool if we could see the syscalls per thread instead. So let's go and do that. But maybe we should fix this and commit this first, because we totally broke top. We gotta fix top before. We can't just leave it broken. I think that's not right. So what are we gonna do with top? Maybe we can just I was thinking we could do like cumulative stats instead. But I feel like it should really have all of the different stats, or all the different threads visible. But I feel so lazy. Okay, let's just deal with it. So instead of having this stats here, we're just going to have to copy things over. So thread data and tid. There's no tid t, there's just int tid. All right. So let's copy all of these things over. Data. Gotta do some high-level text editing here. Yep, and so on, and yep, and so on, and yep. Oh, look at me go. Okay, and then what are we going to put in these? Well, I guess thread dot tid. Stats pid. Maybe something like this will be nice, so we can type like this. Amount shared. Okay, so now we have duplicated all of the stuff, and then instead of doing dot stats, we can just do dot. It seems like thread data times scheduled. Times scheduled, right. And then this thing should not be called processes, it should be called threads. Such unexciting editing happening right now. Okay, and then this thing should be renamed to... And it didn't grok this, so I have to manually do this. Okay, and then username, priority, username, and state. Right, so priority, username is stats username, priority state username. Cool. Maybe that would just work. Wouldn't that be nice? Oh, we have to sync. Okay. Oh, shit. Come on, top. No, 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 no. We are keying them stupidly somewhere. Here. This needs to be a didn't bid. We need... I'm just gonna copy it. It's silly, but these things don't share code in any meaningful way, so it's not easy to figure this part out right now. Plus, this isn't the final design that we want anyway for this stuff, I think. It's kind of a stopgap measure at the moment. So we're just gonna suffer through this, and we will create pid and tid everywhere. So thread tid. Auto pid and tid. Pid tid. Okay, so I think this is going to be good to go. It would be nice if we could move on to doing the syscall counters instead. So now we can see the audio server. We don't see what the thread number is, and these things are a little bit offset because I guess nobody's been updating this app for a while. But we can fix this. State needs to have 2 spaces after it, right? So 1, 2, 3, 4, 2, 3, 4. Oopsie doopsie. Or it can actually say 10 here. That would probably also work because everything is shifted, as you can see. So we need PID and then TID right after. So PID is a really wide field, by the way. That doesn't make any sense. Or maybe it does. It's very ambitious that we would have that long of a running field. I mean that we would need 6-character field for the PID, because I don't think we've ever made it past 1,000 processes. But one day. So let's put TID right after. TID definitely does not have to be that big because it's unique per process, so we can just say 3S is fine. And try TID. And there's no chance that this is going to line up, so we're just going to have to fix that. But let's take a look. Did everything just line up perfectly? No, PID is slightly off, but everything else is good. Nice. So I guess that should be 6S. Everything was fine the way it was. Almost. Not quite. Oh wait, no, this one was all different. Alright. We're getting there. Okay, so here we are. Now we can see the TID and the PID. So we can see that audio server is always up top almost all the time. The secret hidden CPU hog of Serenity is now revealed at last. That's really, really nice. And likewise, you can see it up here too, hogging the CPU. Previously it would be like almost looking like nothing was going on, even though this was going on the whole time. You bastard. I'll show you what that loops looks like, by the way, because there's even a fix me right there. So in the mixer, this runs in a separate thread in the audio server, the mixer, and it's an infinite loop that just takes a lock and then looks if there's something that it needs to mix, and then it checks. If there's nothing to mix, then we just sleep for 10 milliseconds and then go back up here. So this is what it's doing over and over and over and over, as long as there's nothing to do. And it says here, use a wake up of some kind rather than this garbage. And garbage it is. But anyway, previously you couldn't even see the garbage. Oh shit, what just happened? Oh, that was weird. Okay, well, sometimes weird things happen. But I think we are in a good place with this for committing. So let's commit. And let's see, process.h. Let's do that one first. So kernel process for each thread should show the main thread. Yeah. And we have all of this stuff that's kind of dependent on each other, so let's just do it in a bulk. I'm feeling spicy. Kernel plus hey, kernel. Let's say kernel. Expose per thread information in proc. Previously it was not possible to see what each thread in a process was up to, or how much CPU it was consuming. This patch fixes that. SystemMonitor and top now show. Wait, what did PS do, by the way? I already forgot. PS is still kind of confused. But let's leave that as a fix me. Because PS needs to be reworked anyway, because it's really crappy and doesn't show relevant information. SystemMonitor and top now show threads instead of just processes. PS is gonna need some more fixing, but it at least builds for now. Cool. So let's do that syscall count thing. So syscalls are currently logged in the process. These are all the things that we want to log actually per thread. So syscall count, inode faults, 0 faults, and cow faults. So we're just going to copy those over and put them in the thread object instead, somewhere near the bottom, or somewhere next to some other int maybe. I don't know, whatever, right here is good. Okay. And then syscall count is currently updated. Oh, look at these, they're all stuck together. We can take them from here too. Okay, so now we have these APIs for fetching the syscall count and incrementing the syscall count. These are very similar to each other. Thank you, past Andreas, for putting them together like this, so it's very pleasant. And then syscall count and procfs. We just have to, I guess we just have to do like thread dot. And then move these guys down here, plop, and say thread object instead of process object. Okay, so now they should show up in the thread object in the JSON. But we still need to call did_syscall in the right place. So did_syscall currently is here. So when we handle a syscall, then we call process did_syscall, but now we're just going to call current. So it's the current thread. We're going to tell him did_syscall. It's very, very similar to what we were already doing. And then, let's see, then did inode fault. That's here. So instead of current process, did inode fault, let's do current. Did 0 fault. This is actually trivial. And here's the cow fault. Copy on write fault. Okay, and then syscall counts in the process model. We can just, I guess in the process statistics reader, stuff is just going to move into the thread. Right, so we'll take them and put them up here. And when we read them out, then they need to go down here as well. Okay. Cool. And now process model needs a little tweak because these things are all in the thread now. And I think maybe that's it. Let's have a look. It's like, this is a very mechanical programming session, because I'm just like, okay, now we move these things to here and these things to there, and like, but, you know, sometimes that's what you gotta do. Right, forgot about top again. So it's a little bit weird that basically a thread has identical memory information with the other threads in the same process, but it has unique CPU usage, unique thread state, unique syscall count, fault count, stuff like that. But it's also pretty logical, and I guess it probably matches what other systems do. Although I haven't actually looked at a process monitor for a while. Why don't we look at one here? Where do I even find one? System tools? I'm not very knowledgeable about this desktop that I'm using. I just got one that seemed not horribly ugly, because there's no shortage of horribly ugly desktops on Linux. And this is not beautiful to me, but it is not ugly, at least. If you stare at it all day, you know. So definitely there have this tree view kind of thing going on here. But I get the feeling that these are not threads, but rather processes, and they're like parent process. You see the child processes, so you're probably not seeing the threads here. These are my processes. What if I wanted to see threads? Maybe I can see threads, I don't know what to look for, and whatever. Okay, so now if we sort by bit, and here's audio server, and we can see that this secondary thread, the mixer thread here, keeps making syscalls. It's very noticeably doing 100 syscalls per second, which makes sense since it's sleeping every 10 milliseconds. So it's really cool, because you can see that this main thread is not doing any syscalls, and this one is. Likewise here with the Windows server, you can see that the CPU monitor thread not making that many syscalls, whereas the main thread is main thread, or the compositor thread, or whatever you want to call it. But yeah, so this is pretty neat. Pretty neat. I have to say I'm very happy with this. I'm thinking, like, is there something else I would like to show here? I like that you can see that this thread is sleeping and this one is selecting in the same process also, because previously you could only see the state of the main thread. Oh, okay, what the heck did I click on? That's triple faulting again. I don't know what I was clicking on, but something there does not like me. I guess when we try to look into something, then it just falls apart. Anyway, we don't have to solve everything now, so we're just going to keep ignoring that, and we're just going to commit this instead. So, kernel, track syscalls, and page syscall and page fault counters per thread. Make syscall counts and page fault syscall counters and page fault counters per thread. Yep. Now that we show individual threads in SystemMonitor and desktop, it's also very nice to be able to see It's also very nice to have individual counters for the threads. Aha. Okay. Maybe we can actually put its here. Although it feels weird to have its like that. Let's just keep it on the next line. Important stuff. And I feel like I had a bug open about this. Well, let's just search for it. Maybe it was called something like Threads Process Manager. Make it possible to see threads somehow. Look at that. We are closing a pretty low number bug that I opened back in May. Wow. It's been a while. Only took me 6 months to deal with this. It would be cool to be able to see threads. No tree, though. Not today. Just somehow. Okay, so we're gonna say that this commit right here is gonna have a little fixie thingy in it. Edit, commit, amend, fixes, 66. Rebase, continue. All right, so let's do a full build just to make sure that everything's good, because now I got a little paranoid. But I think we're basically in the clear here, and yeah. And I think this is also going to be the end of the video. So if you made it this far, then I thank you for watching. And I hope you saw something interesting today. And thank you for hanging out. Really appreciate the company. This is a weird little adventure that we're on here. So it's really nice of you to hang out. And I don't know what else to say, so have a great day, and I will see you next time. Bye.